Welcome to Granite Research's Industry Expert Series. Investment research can be downloaded at granite-research.com. I'm your host, Rob McGuire, an analyst covering LSB Industries, NYSE ticker symbol LXU. And I'm pleased to be joined today by Dr. Jakob Krummenacher, Director of Clean Energy at LSB Industries, who will be discussing clean ammonia. Good morning to everybody. My name is Rob McGuire. I'm an analyst with Granite Research. I want to thank you for joining us today for our expert series call with Dr. Jakob Krummenacher, Director of Clean Energy at LSB Industries. This call is being recorded. There'll be a link to the replay available at graniteresearch.com or at LSB Investors Relations page. And the Granite Research website is granite-research.com. Also with me today is LSB CEO, Mark Berman, and Vice President of Investor Relations, Fred Buonocore. Mark's going to have some opening remarks here, and then he's going to introduce Jakob. And with that in mind, Mark, would you take it away?
Sure. Thanks, Robin. Good morning to everyone. I'll be really brief because I know everyone's really interested more in just clean ammonia and what's going on. There is a global push to decarbonize, as everyone's aware of. There's a big focus on both low carbon hydrogen and low carbon ammonia. And as an ammonia producer, and quite frankly, the fifth largest in the US, we're very focused on that. We started our efforts about 3 years ago. Initially, it was, I'd say, learning more about what the possibilities are and the demand, potential new demand that was out there. And as we continued to really develop a focus for us and even think about a couple of projects and what we could do on our site, we ultimately decided that it wasn't a part-time job for me and that we needed to really bring on someone who had both experience as a chemical engineer so that there's a knowledge base on what we can and can't do with our existing facilities, but even as we think about new facilities, the person really had to have that kind of background, but also be very commercial. So Jakob and I started talking a couple of years ago, and it's now what, Jakob, about a year and a half since you joined us. And Jakob leads our efforts on clean energy. I'll let him give a little bit about his background, and then we're really excited about the opportunity. We think that it's not a question of will new demand really materialize. It's really a question of timing. And when will that demand materialize? And as new demand comes on, clearly there'll need to be more supply to really support that new demand that will be out there in the marketplace. So with that, Jakob, why don't you maybe give a little overview of your background and then get right into the fireside chat and the Q&A.
Excellent. Yeah, thanks, Mark. Thanks, Rob, for hosting this call as well. Like Mark mentioned, I'm Jakob Krummenacher, Director of Clean Energy. In my background is chemical engineer by training, but I spent most of my career in the energy world. Actually, most of that first 12 years, I spent it in the oil trading with BP in an oil trading bench, doing analytics, being the lead analyst. And in the last 4 years, I was in the marine fuel bench before moving into the nitrogen world. And once you move into the nitrogen world, I was looking forward to do a different commodity, more helpful as it feeds, help grow crop to feed the world. But within a year of moving into the nitrogen world, the whole talk about hydrogen and ammonia as clean energy products started. And when you are the only energy guy in a fertilizer company, you're automatically employee number one of a clean energy team. So I started doing that for CF and before moving on to LSB after having several conversations with Mark. So I want to make this a little bit more interactive. So if you do have any questions along the way, just raise your hand and either Rob or Fred will address you. And please mention your name and the firm that you are with before asking the question so that it's on the recorded line as well. So without any further ado, let's go ahead and start. Fred? Yeah, so first slide here, I added these in order to remind ourselves as to why the world cares about decarbonization and why we're doing these. And the real issue is that we have a 40 gigaton carbon problem globally, meaning that 40 gigatons of CO2e or GHG greenhouse gases are emitted every year into the atmosphere on a net basis. So when you talk about the Kyoto Protocol, the Paris Agreement, they all want to reduce this 40 gigaton number. But where is it coming from? If you look at the chart on the right, you can see the countries that generate the most greenhouse gas emissions. And you can clearly note that between China and the US are almost half of the world's emissions. So any kind of agreement, any kind of protocol that gets instituted in place will not work if the US or China are not part of it, because then you're really only addressing 20 gigatons instead of the full 40. The chart on the left shows the industries or the sectors that generate these CO2 emissions. You know, a lot of it, a quarter of it is electricity and heat production, you know, to keep our homes warm, to keep our houses power and our buildings power. You burn a lot of fossil fuels to do that. There is also transportation, you know, cars and buses and trains and airplanes. They account about 15% of the global emissions. Ammonia production falls under the industry sector that accounts for about 21%, but ammonia on a global basis, even the 187 million metric tons that get produced every year, they're only responsible for about 1.2% of the global greenhouse gas emissions. So people sometimes ask, you know, is it really going to make any difference if you're looking at 1.1% reduction by decarbonizing ammonia? But the thing that you need to look at is like, what are you going to be using this low carbon ammonia for? And as people think about using it for fuel, well, if you're looking at about for as a fuel for power generation, then it's going to be reducing that big 25% slice of electricity and heat production. If you're using it for marine fuel, then it's going to reduce a big chunk of the transportation slice. And also, if you continue to use it for conventional uses like agriculture, it will also reduce that 24% on the agriculture, forestry, and land use. At the end of the day, when you look at this pie, about 3/4 of it are energy related. You know, we burn fossil fuels to produce electricity, we burn fossil fuels to generate heat, and that heat keeps our home warm, or we burn fossil fuels as a transportation. In the industry sector as well, we burn a lot of fossil fuels to generate heat, and that drives chemistry. So all in all, 75% of that pie is related to energy. So it's an energy problem, and only energy can solve. So let's look at the next slide, Fred, please. So if we look at energy really can provide three things for societies, right? It can provide heat, it can provide power and light, and it can provide mobility. And you can see most of it for the last 130 years or so, we've been developing this carbon-based energy society. We use fossil fuels for generating electricity, for heating homes. We use fossil fuels for power and light. We use fossil fuels for mobility, gasoline, diesel, bunker, marine fuel, jet fuel. And it's been transitioning in the US right now. For example, the electricity sector uses about 22% of renewable power, which is a part of the transition. You know, it's going to take some time to get there. What does that look like in the future? Well, more of all of the above, more of renewable electricity, more of renewable natural gas, biomass, nuclear should be part of the equation as well. But one thing that you see in common, whether it is heating, power and light, or mobility, is that ammonia and hydrogen, the low carbon kind, are all featuring in all three buckets of the energy sector. So they're about to become a big fuel or feedstock for the energy sector in all of its uses. Next slide, please. When we look at the demand for hydrogen and ammonia, which is the chart on the left, In 2020, the world made almost 75 million metric tons of hydrogen. About half of it was used in the refining, mainly used in the refining sector. It's usually made from natural gas via steam methane reforming, and then refineries use it to remove sulfur from crude oil or from fuels. And they use it, in the hydrocrackers and hydrotreating as they make smaller molecules, like when you chop off, oil molecules into diesel, gasoline, or other products. Then you're short hydrogen and you need to replenish that, and that's how they use it. About a third of the hydrogen is used to make ammonia, and that third of 75 million metric tons is actually producing 187 million metric tons of ammonia today. And then the rest is methanol, steel, and other applications as well. Ammonia, as you know, about 80% is used into the fertilizer market. Most of it not as direct ammonia application, but it's some kind of shape of a downstream product, mainly urea on a global basis, although in the United States, the main product of use is UAN. And about 20% of the global ammonia is consumed in industrial uses, explosives, refrigerant, plastic, emission abatement, chemical feedstock, and other uses. So when we look at the projections of where things might go, you have, conventional applications, industrial, and ag have been growing about 1.4% on a global basis every year. So we expect that to continue again over the next decade as we look into 2030, and that will represent about 20 million metric tons of incremental demand from 2020. But what we're seeing today is that people are looking to use ammonia as a power generation fuel in place of coal, particularly in Japan and South Korea, and that's expected to have potentially about 7 million metric tons of new demand of ammonia as a fuel. We're also looking at companies that are testing today marine engines that run on ammonia. If you put ammonia on a marine engine, you end up with zero carbon emissions on that engine. And if that ammonia was made in a way that was low carbon or no carbon, then you have an end-to-end fuel that has zero carbon emission. And that is very attractive for the marine industry, which we're expecting to be somewhere around 5 million metric tons in 2030. If you look at 2050, everybody has all kinds of projections, and the way we put this together is that we look at everybody's forecast, the IEA, International Energy Agency. We looked at IRENA, CRU, Argus, and others, and some of them have very rosy forecasts that is probably twice as much as what we have here. But we wanted to put something that is more realistic, and we feel that that is within reach. And even then, it's basically asking for doubling the capacity of producing ammonia on a global basis over the next 25 years or so. So it is a huge increase in demand. So how do we make these kind of products? So let's look at the next slide, Fred. So people a while ago, when they started talking about hydrogen and the different essentially the environmental attributes of the hydrogen that you make in terms of the carbon intensity, they decided to label the different processes based on colors. So if you make hydrogen, like most of the hydrogen is made today from steam, via steam methane reforming from natural gas, then they decided to call that gray, and you have a carbon intensity of about 10 to 1. So 10 kilograms of CO2 per kilogram of hydrogen if you make it that way. If you continue to make it that way, but you somehow capture some of that CO2 and permanently sequester it, prevent it from being released into the atmosphere, then you can call that blue. If you make a hydrogen in a process that is entirely carbon-free, like taking renewable power and splitting water via electrolysis into hydrogen and oxygen, if you make it that way, they decided that's green because that's the ultimately cleanest way of making hydrogen in terms of carbon intensity. And then everything else is somewhat in between. If you make it from methane, but you don't release CO2 and you instead collect the carbon black, they call it turquoise. If you make it in an electrolyzer, but instead of using renewable power, you use nuclear, power, then they call it pink, and so on and so forth. But the world is kind of moving away from this because the big issue with this color-coded labeling of the hydrogen, which ultimately also represents the labeling of the ammonia as well. The main problem with this is that it doesn't really say much about the carbon intensity. Take blue hydrogen, for example. I could capture one of those 10 kilograms per kilogram of hydrogen and essentially my carbon intensity drops to 9, and I can call that blue. Or I can capture half of it and drop the carbon intensity to 5 kilograms of CO2 per kilogram of hydrogen, and it's still blue. So it doesn't really say much about the actual carbon intensity. So we're going to be moving from this to a carbon intensity world. So you're going to have your process, and you have to be open about your operation in terms of carbon emissions so that people can trust the carbon intensity of your product and potentially be certified that way. Next slide, please, Fred. So here's why it's important to go low carbon. This chart has the levelized CO2 emissions of the fuels from the life cycle. So if you start at the left, these are grams of CO2 generated per megajoule of fuel. So keep in mind that a megajoule is different on every fuel, right? A gallon of diesel will have a lot more energy than a gallon of ammonia, and a gallon of ammonia will have a lot more energy than a gallon of liquid hydrogen as well. So if you look at this on the left, you're looking at coal, a good power generation fuel, and you're looking at bunker fuel or marine gas oil, and then ammonia and diesel. You can see that ammonia and diesel are very similar in terms of emissions, about 100 grams per megajoule. The big difference, though, is that the blue portions of these bars are the emissions generated while you manufacture the fuel, while the gray portions of the bar are the emissions generated while you burn the fuel or you use the fuel. So you can see that diesel, for example, 20% of the emissions are generated at the refinery when you're cracking down the oil into the different products in the refinery. You only emit about 20% of the total fuel emissions. 80% of it are generated on board of your diesel truck, on board of your tugboat, or whatever you're using it as a fuel. So it's a much more difficult proposition to decarbonize that type of fuel. A, because it's flue gas, so it has low carbon concentration, low CO2, about 7 to 8%. But B, it's moving. So you have to have some kind of a movable carbon capture system if you're going to go after that. Ammonia, on the other hand, 100% of the emissions are generated at the ammonia plant. And technically, they're generated at 3 stacks: the primary reformer, the secondary reformer, and then the high purity process stream that emits the CO2 from which we remove the hydrogen from the methane. So as you can see, if you take ammonia, for example, a conventional SMR today, about 60% of that CO2 emissions comes from the process side. And because we're interested in removing as much hydrogen as we can from that process side so that we can make the ammonia, we end up with a high purity CO2 stream, which is about 96% and 4% water. If you can capture that CO2, like what we're trying to do at El Dorado, we're going to capture that CO2, we're going to remove that 4% water, we're going to compress it and inject it into the subsurface, and that will leave that ammonia plant with a 60% reduction on the carbon emissions. So essentially we'll go from 102 all the way to the right to 40 grams of CO2 per megajoule. And you can see other fuels are there too: gray liquefied hydrogen, gray methanol, LNG, a little bit better than ammonia. Corn ethanol is 57%, that's a renewable fuel. But once you make blue ammonia, you can find the technology to continue to capture the combustion emissions of the CO2. You can bring it all the way down as close to zero as possible. Or if you use ATR technology, you can capture more of it, 95, 98%. But once you go down to zero, then people ask the question, well, if you make hydrogen before you make ammonia, why does the world want to use ammonia instead of hydrogen? And that little table tells you some of the advantages of ammonia over liquid hydrogen. Number one, it has 2.5 times the energy density per volume than liquid hydrogen. So if you're shipping around liquid ammonia or liquid hydrogen in a vessel, you're shipping 2.5 times more ammonia for the same volume. So it's an efficient way of shipping a fuel. The other issue is that to keep hydrogen in the liquid phase, you need to be about 400 plus Fahrenheit, negative 400 plus Fahrenheit, which is a really, really low temperature, very expensive way of keeping things cold. Ammonia, you only need about minus 30 Fahrenheit in order to keep it in the liquid phase. And then there are issues with the flammability, right? Hydrogen is highly flammable. Ammonia, on the other hand, is not as flammable. It's toxic, more toxic than hydrogen, but we've been using ammonia for over 100 years, and we ship around the world safely. We ship over 20 million metric tons today, although the last couple of years has been a little less than that because there's very little being shipped out of Russia. But the flammability of hydrogen is an issue. For example, Kawasaki Industry built last year the first ever liquid hydrogen carrier, and it's used to take hydrogen from Australia that is ironically made out of coal to Japan and is blended into the nat gas pool in order to use for power generation. That vessel costs about 4 times the price of an LNG carrier, and it carries only 1/3 of the energy content that an LNG carrier carries. So it's a very expensive way of shipping hydrogen. Not to mention that on a 2.5-week voyage from Australia to Japan, about 2% of the cargo gets lost because they cannot just keep compressing and cooling to keep it in the liquid phase. So it just vaporizes. And about 4 months ago, the vessel caught on fire. Leaving Australia, going to Japan, it was, I think, the 4th or the 5th voyage. And it caught on fire. And the dangerous thing about hydrogen is that when it burns a colorless flame and a smokeless burn as well. So people did not know they were on fire until they started looking at the pressure drops in the vessels, and then the temperature gauge is going off. And that's how they determined they were on fire. So luckily they had some pretty good safety protocols on board, and they got put out and everything was fine after that. But it's some of the issues that we need to be worrying about when using hydrogen instead of ammonia as a shipping fuel around the world. Next slide, please, Fred. So we're working on a couple of projects, LSP, one in El Dorado, Arkansas, where we're going to be capturing the processed CO2 from an ammonia plant that is existing today. And we're going to clean it up, remove the 4% water, and pressurize it, turn it into liquid CO2, and then permanently sequester right under our land. Our pipeline is going to be about 0.3 miles. It's going from the production site through the parking lot to the south of the property. We have 1,400 acres of land, so we determined, or our partner, Lapis Energy, determined that there is enough storage capacity for about 50 million metric tons under our property. So in essence, the 450,000 metric tons of CO2 we're capturing annually, or we're going to, starting in 25, we could do that for technically 100 years before we run out of storage space. This project is going to be very economical for us because we're going to be selling a product that today we're venting. So the 450,000 metric tons a year are expected to increase EBITDA by about $15 million annually. The plant will not go down to zero in terms of carbon emission because you still have flue gas CO2 being emitted into the atmosphere. But there is a lot of company working on different technologies of how to capture that economically. And that will be a game changer because once you capture the flue gas and you can put it through this process of dehydration and compression in order to permanently sequester it, you can convert this conventional ammonia plant into a zero or very close to zero carbon emission plant. And that can be very beneficial when we're looking at the transition into low carbon, zero carbon, and still be able to use existing infrastructure. So in terms of timeline for the project, let's look at the next slide, Fred. So here it is. In mid-February, our partner, Lapis Energy, they submitted a Class 6 permit application to the EPA, Region 6. Within about 3 weeks, in early March, we received a letter back from the EPA saying that the application is fully complete. All the documents necessary for them to review are there, and they're moving into the review process. So we don't know how long that's going to take, but at least it's good news that within a short period of time, they came back and deemed the application fully complete. Right now, we're in the midst of the FEED study, determining what needs to be done as far as engineering and equipment and installation, and detailed engineering should start pretty soon. And once that starts, and depending on what we hear from the EPA, we'll be in a position to start ordering long lead items like transformers, compressors, and that type of equipment that will be needed. So all in all, we're in pretty good shape to start injecting sometime around the middle of 2025. The expectation again of the project is that it will qualify for the 45Q tax credits, which the IRA, or the Inflation Reduction Act in August of 22 that got passed, increased it to about $85 per metric ton on year one, and then it will be escalated by inflation on an annual basis for the first 12 years of the project. Next slide, Fred. We're also working on a green ammonia project on our other facility in Pryor, Oklahoma. Why Pryor? Well, Pryor is in close proximity of a multiple of wind and solar developments that are ongoing, so it's easier to get renewable electricity in that region. So right now we have a conventional ammonia plant that produces 230,000 tons of ammonia a year. The idea is that we're going to reduce the amount of hydrogen that is made in the steam methane reforming unit. I'm going to replace that hydrogen with electrolytic hydrogen from electrolyzers. And that is going to turn the facility from 230 of gray to about 200,000 tons of gray ammonia and 30,000 tons of green ammonia. We completed a feasibility study, but right now we're working with EPC firms and looking in more detail at the technology, because it's there are huge differences in terms of the costs and also differences in terms of the risk associated with the scale-up of solid oxide versus alkaline units. So we're expecting to make FID very soon, sometime over the next couple of months, once we hone in into a single technology and we make a selection on the EPC firm, and then we'll be moving forward. A project like this can move really quickly. It doesn't depend on a Class 6 permit, but it does have issues in terms of some long lead items like transformers, rectifiers, hydrogen compressors, for example. Those can be on a 12 to 18 month lead time. And so we'll be dependent on those for the startup. But we still think that there is pretty good opportunity to start up sometime at the end of 24 or beginning of 2025 for operations in these. Next slide, Fred. Yeah, and then finally, we have some clean energy projects ongoing. We're purchasing currently renewable electricity for about 10% of El Dorado power, looking to expand that too for other facilities. We have the low carbon ammonia or blue ammonia project at El Dorado. We have the green ammonia project at Pryor. We're also working on expanding our N2O abatement at Cherokee in particular, and that will continue to reduce our Scope 1 emissions. We have also clean energy developments ongoing right now. We're looking at the options or opportunity of using renewable natural gas as a feedstock. And we're also looking to continue to buy more renewable power for our operations. And then we're working on developing our clean energy strategy, which is, what's next, basically. Can we pursue future growth opportunities in no carbon ammonia and hydrogen, including new facilities or expansion of existing facilities today? And that's where we are. It's been a great journey. It's been very high speed kind of journey that we've done in the last year and a half here at LSB. And it's all positive, and we expect that our customers, our counterparties all value what we do in terms of the low carbon front.
Jacob, that's great. Thank you so much for that presentation. We're now in the Q&A portion of the call. I would encourage everybody to step forward if you have any questions. Fred can always flip back to a slide as a reference. But with that started, Scott, could you unmute your line, Scott McLeod, and ask your question?
Yeah, thanks so much. Thank you for all this. But my question is about the El Dorado project. Sorry. What do you think the costs are going to be to get that up and running and fully functional?
So to be clear, the way that the deal was structured with Lapis Energy is that there is no capex from LSB at all. Our partner will put up the entire capex for the capture facility, the dehydration plant, the compression of the CO2, and the injection wells, along with the monitoring wells that are required for the EPA. So it's going to be a zero capex kind of project from the LSB point of view.
That's a good use of cash. Okay. My other question, obviously you've got two big projects on hand here, but where do you see, because in last part of your slide there said that you see future growth opportunities. Do you see that in like mergers and acquisitions, maybe purchasing something, or do you guys have anything on the horizon that you're thinking about at this time?
Yeah, so look, we're always looking at new opportunities, whether it's M&A opportunities, like the recent sale of Incitec Pivot's Waggaman plant to CF Industries. We certainly would have liked to potentially purchase that asset. That would have been a good asset for us. So we're always in the mix at looking at some of these assets. And then, we look at a lot of new builds announced. So there are a lot of announcements that I'm sure either Rob or someone will ask a question about. But most of those have realized that they need a partner that's got ammonia expertise. So the ability to understand how to design and build and construct a plant, but also how to operate and handle and store and ship what is in essence a hazardous material. So we are in conversations with a number of folks about some of the new build announcements, and yet to be determined whether we participate in any of those or some of those.
One thing to add on that is that developments of clean energy strategy also includes the potential expansion of existing facilities. Take for example our El Dorado site. We have 1,400 acres. We have a small plant that only occupies probably 100 acres, if that. So there's plenty of land for expansion. You're going to have a Class 6 well potentially in operation in 2025. We got ample subsurface storage that you can build another ammonia plant, and already with the capture in place. Now that site also is connected to the New Star pipeline, and the New Star pipeline can run both ways. It can run north and it can run south. So there is the potential of developing terminals down south, and then you can send blue or low carbon ammonia to markets that will have more value for a clean product than if the local market isn't ready at the time.
I'm going to encourage everybody to step up. Please ask a question if you do. And in the meantime, I'm going to have a couple of questions that I ask along the way. So please don't hesitate to interrupt me. So Jacob, with the supply of clean ammonia, we're seeing a lot of, or I'm thumbnailing approximately 9 million metric tons of new capacity planned to come on in the US in the 27-28 timeframe. Can you just discuss the supply of clean ammonia, and will that be created ahead of demand? Or do you think, how do you see all that coming together?
Yeah, good question. One thing that we have to be aware of, and I think it's slide 7 in this packet, it clearly says that in order for this to be beneficial environmentally, you have to use some kind of low carbon ammonia type, right? If you use conventional ammonia, then you're not different than using diesel at that point in terms of CO2 emissions. So that means that only plants that will have low carbon ammonia or lower carbon intensity ammonia are the ones that could supply ammonia to this new energy front, right, or new energy market. And then the other piece of the pie to remind ourselves is that the ammonia as energy market, whether it is as a marine fuel or as a power generation fuel, is going to be a replacement fuel, meaning that there is already a fuel in place. And how quickly that grows, that replacement, will depend obviously on the infrastructure, on the supply of the product, but also, and even more importantly, about how quickly the governments that are looking to do that, and I'm looking at Japan and South Korea in particular, how quickly can they set policy in place to allow this demand to move on and replace the existing carbon-based fuels? So yes, right now we're looking at all the ammonia plants being announced in the Gulf. A lot of them will be some kind of, at some level of low carbon intensity, depending on which one you're talking about. And everybody's concerned about that. Obviously, some of them will be delayed, some of them might not make FID. But let's keep in mind that Japan can have a control in terms of policy of how much that demand is going to grow. And they're going to play with that in order to, they cannot exceed the supply, because we mentioned that conventional ammonia cannot be used for this. Otherwise, the environmental attributes or benefits are kind of wiped out. So they can go at a pace that meets that supply, and then essentially kind of balance the market. Another point of concern that Japan has is that they don't want to be a disruptor of the ag market. Like if they increase demand all of a sudden, and there is a shortage of ammonia in the ag market and prices go up, they don't want to be seen as being blamed for doing something like that. So they're going to pace themselves at a good clip. Right now, all eyes are on JERA, is the largest utility in Japan, who are going to be doing a real world-scale application test of ammonia in a coal-fired power plant in Q1 of 2024. They're going to run 1 gigawatt power plant with 20% ammonia and 80% coal for a month. And for that test, they need 40,000 tons of ammonia. And then the idea is that if that's successful, they're going to continue running at 20% ammonia, 80% coal all year round, which means that that's 500,000 tons of ammonia demand at 20% for one power plant. And JERA has 14 power plants that they're looking to do these for. So, all eyes on that test, and that will determine how quickly, the Japanese policy gets set, how quickly the demand gets developed. And obviously, we also need to develop infrastructure or how to deliver these products, terminaling, how to store them, how to, there's a lot of tanks and pipelines that need to be put in place for these to grow as well.
Hey, Rob, one thing I would add, there are a lot of announcements, but, to build, a world scale ammonia plant, so call it 1 million to 1.2 million tons of production a year, depending on the infrastructure that's on site or lack of infrastructure, you're talking about $2 billion to 2.3, $2.5 billion to build. So we're talking about significant capital, most of which would be debt financed, but still a significant equity check that needs to get written. From our conversations with folks that are out there, I mean, when you've got funds or CapEx requirements that are that large, most people will not greenlight a project until they have, I'd call it 80% or more of the production spoken for in long-term priced offtake agreements. So I think what we'll see is there's a lot of announcements, but it's possible we could have one or maybe two plants that go spec. If you build it, they will come. But more than likely, everyone's chasing the same initial buyers, and those folks that actually get not letters of intent with buyers, but ultimately real contracts will be the facilities that get built. Also point of reference, I mean, back in the 2012 to 2015 timeframe, when natural gas prices here in the US started to drop really precipitously, there were about 36 announcements of new facilities, new ammonia facilities and upgrading facilities that were announced, and 7 plants got built. So again, I think, announcement to final investment decision and financing a project going forward, there's a very large gap there, and there's a lot of hurdles to really hit until you actually have the capital to go forward with a project.
That's helpful. Thank you, Mark. So Jakob, I'm just going to move on to a couple other questions. In terms of the technology, do the NOx emissions remain a problem when burning ammonia?
Yeah, I get that question from time to time, and it's very interesting because do you know how coal-fired power plants abate NOx? They use ammonia. So they mix ammonia in the exhaust stream, and they do either a selective catalytic reduction or more than likely a non-selective catalytic reduction, where ammonia reacts with NOx to make nitrogen and oxygen, or nitrogen and water. And so essentially reducing completely NOx. So yes, to answer your question, yes, if you're burning ammonia, NOx is a concern. But you also have ammonia on board that can treat that exhaust effluent and reduce it to the same way that you do in a coal-fired power plant today. So you will have that in place. Now, the NOx is happening because of the temperature, right? And more importantly, when you're looking at ammonia engines, ammonia has a very high initial temperature requirement, which is good because it doesn't explode, but bad because it doesn't explode inside the internal combustion engine when you want it to explode. So you're typically going to be using a primer fuel, and Wärtsilä is the largest marine engine manufacturer in the world. They're using diesel as a primer fuel, so they put about 2 to 3% diesel into the cylinders to reach that temperature of ammonia and help it do a complete combustion. And they can play with the ratios and the temperature to get the NOx down as much as they can, and then abate the rest with the ammonia that they already have on board. MANI, the second largest marine engine manufacturer, is doing a similar thing, but instead of diesel, they decided to use compressed natural gas, and they do about 5% into the cylinder, and that's the same thing. Now, what it means is that these engines are now not 100% carbon free because you have 3% diesel, 5% natural gas. But the idea is eventually when people develop systems like cracking ammonia into hydrogen, which a company called Ammonia has one of those prototypes in place, and they're being already using it in real world applications. You can crack some of that ammonia into hydrogen and then inject hydrogen in the cylinder, which means that you don't have to worry about storage of hydrogen. You're just going to make it and use it. And hydrogen obviously has a high flame, it's the most flammable molecule. So it will create the temperature and help with the flame speed to fully burn the ammonia and further reduce NOx. So that's kind of the development on the ammonia engine.
Thank you, Jakob. What's the cost of using ammonia relative to the conventional fuels that are out there for power generation, bunker fuel, and any other applications that you can speak to?
Yeah, and good question. The short answer to that is we still don't have all the pieces of the puzzle in order to give you a complete answer. But take, for example, diesel. One of the markets that we're looking at in particular is the inland waterways in the United States, where there is a lot of tugboat traffic taking things up and down the Mississippi River in particular. So they have been running on low sulfur diesel or ULSD #2 for a while. So if diesel trades at say $2.75 a gallon, then the cost per megajoule of that compares to the cost of megajoule of ammonia, if ammonia trades at the long run average of say $350, $375 a metric ton. So that's kind of your base comparison. Now, if you're making ammonia in a low carbon way, you're going to increase the cost of making it a little bit, but you don't know what that compares to, say, if the government institute a carbon tax, and now if you're going to burn diesel fuel, you're going to pay a penalty because of the CO2 emissions. We still don't have that, whether it is a carbon tax or whether it is a company wanting to abate that and going into the markets to buy carbon credits or carbon offsets in order to reduce that. In either way, that cost will be significantly higher on the diesel side than the ammonia side, because you're making it in a low carbon way. So we still don't know all the pieces in order to give you a straight answer, but as a baseline, if you're looking at diesel of $2.75 a gallon versus ammonia at $350 a ton, those are like compared to each other in terms of in the megajoule basis of energy.
I appreciate that. Thank you. And you showed your slide earlier, but I didn't see biofuels on it. We hear a lot about biofuels. Can you just talk about biofuels versus using ammonia in our future?
Yeah, so still, I think ammonia as a marine fuel is very viable. Is large quantities. The vessels are very little man operated. I mean, you have a kind of a crew of a handful of people on a very large vessel. Using ammonia in a vehicle, a passenger vehicle, it could be a much more difficult proposition. It's kind of like hydrogen as well. It can be very controversial, simply because, like, let's say you're driving on a tunnel and there is an accident and then there's a spill. It could be deadly in the case of ammonia because of the toxicity. In the case of hydrogen, it could be deadly because of the explosivity associated with it. So I think that would be a kind of a difficult proposition of using ammonia on a smaller application. I think electric vehicles are much more appealing, and there's been growing quite rapidly as of late. So that is a difficulty. But one thing that the low carbon fuel or the biofuel market has that is kind of presenting an opportunity, a learning opportunity for this low carbon ammonia market to be developed is in terms of the low carbon fuel standards, for example, where a state like California, they go around and they look at all the ethanol producing facilities and they rank them based on the carbon intensity. And they give them kind of a pass or certificate that says you are allowed to sell X number of tons based on these calculations into the California market. Now, that doesn't mean that the tons are produced at that facility. The certificate comes from that facility, but the tons can be going from a closer facility to avoid unnecessary logistical costs, right? The same can happen in ammonia. When we're looking to certify this low carbon ammonia, I envision, exactly the same market where you're going to, because you can't differentiate between low carbon ammonia or conventional ammonia by looking at the product itself or doing tests on the product itself. They will be the same ammonia ton. What's different is the process by which it was made. And if you can separate that on a paper certificate or a virtual certificate, then you can trade it around like you're trading ethanol with the low carbon fuel standards today, or like the renewable energy companies are doing with the REG on the electrons that come from solar or wind facility as opposed to nat gas fired power plants.
That's helpful. And you mentioned something there. Who is developing the standards for the certificates that you're talking about, here in the US, and possibly are there any global standards that are going up to allow these certificates to be traded across borders?
Yeah, there are several entities looking to do that. Obviously, there is the hydrogen certifying entities in Europe, like IPHE or ISO. They're all looking to back down integrate into ammonia because they already have a hydrogen certification kind of in place. Not very widely used today, but it's in place. But you're looking also at all the ammonia companies or organizations, for example, the Fertilizer Institute in the US or Fertilizers Europe in Europe. They're trying to do the same thing. They're trying to say, okay, what does an ammonia producer need to supply in terms of data to a third party in order to certify that kind of low carbon ammonia. And we're members of the Fertilizer Institute, and we're working hand on hand with them. And right now we're starting a pilot program using the data from our El Dorado facility to tell us what is the carbon intensity today and how low it's going to go once we have the carbon capture project in place. And then that will be a way of saying, okay, if we can get a third party now to come in and vet those numbers, then the next step will be the issuance of a certificate and then a trading mechanism, like a registry that can keep track of all those certificates. We're also members of the Ammonia Energy Association, and the Ammonia Energy Association, being a global association, is very much interested on that. But it's going to rely a little bit more on the different regions to do certain level of kind of moving the project forward before they come in and they do more of a macro level, so that then you can trade with Japan or you can trade with South Korea. But that's kind of the idea that you know, a certifiable ammonia ton should, the environmental attribute of that ammonia should be trading separate from the ammonia ton, so that you can avoid unnecessary costs and emissions as well. Because take, for example, our El Dorado tons, we can put them on if we develop an ammonia terminal in the south, we can put it on a pipe, load it on a vessel, take it to Japan, or Japan can buy the certificates from that facility and then buy the ammonia from Indonesia, say. And there is a big difference on the CO2 emissions associated with the vessel shipping the ammonia from the US to Japan versus Indonesia to Japan. So there's a lot to gain in terms of CO2 emission and in terms of cost as well.
Thank you. Please, anybody who has any questions, please jump in. Jakob, can you explain the economic benefit of the 45Q and 45V tax credits, and then perhaps even elaborate a little on how the Inflation Reduction Act boosted those credits, or at least the 45Q, what that might mean to LSB as well?
Yeah, let's start with the 45Q. The 45Q is not new, right? It's been around for quite some time. It started at very low levels and sort of like didn't create that much of a push to decarbonize, because the numbers were kind of low for most users or most emitters today. So I think the government realized that, and they really want to make a push to develop these, and that's why it's only for 12 years, and they made it up to $85 a metric ton. And they did some calculations, and they estimated in order to get a good chunk of the industry to decarbonize, we need this level of support. But the truth is that it's not the same for everybody, and it doesn't work the same way for every emitter. For example, the smaller you are, so when you're looking at a carbon capture project, there's three key things that will drive the economics of the project. Number one is the quality of the CO2. The highest the purity, the better. The less cleaning that you have to do, so the most cost effective to capture that. So hence the process CO2 of ammonia production is very suitable for this. Number two is the quantity of the CO2, right? If you have a project for 2 million tons versus a project for 1 million ton, it's not too much, twice the capex. It's somewhat more, but it's not double the capex. And so you benefit from the economies of scale. And then number three is the distance between the emission point and the capture point. If you need to build a 50-mile pipeline, then most projects won't work. a 50-mile pipeline at a rate of $1 to $3 million a mile. It makes it very costly. Not to mention that it would also add timing for the project itself, because getting all the permit, getting the right of way in place, dealing with multiple landowners, it just adds a lot more complexity to the project. So $85 a ton works for certain projects. Our El Dorado project, because we are right sitting on the same information, very short pipeline. Even though our volume is not large, it's 450,000 tons only, but it is high quality of CO2, high purity. So it has a lot of the check boxes to make it work. The other piece of the pie is that, let's say you have all these three attributes to make the project work, but you are a company that is small and don't have the balance sheet or the tax equity within your balance sheet to monetize the tax credits. Then you're forced to go to the tax equity markets. And what happening there today is that tax equity investors are taking about 15% of the 45Q in order to monetize the credit. So right from the beginning, you're taking $12 out of the 85 or $12.50 out of the 85 in order to, and then you have less money going to the actual project. So that kind of would discourage a few of the potential emitters that can have capture facilities in place. The 45V is still not much information out there. I mean, as you know, the DOE hasn't set yet the requirements in order to qualify for those projects. So we're still waiting to determine on how much effort you need to put in order to say, hey, I qualify for the full $3 a kilogram of hydrogen.
Thank you. Tim Shatar, do you have questions you'd like?
Yeah, thanks, Rob. Just related to that 45V question, that was something I was curious about. What is the economic benefit of the Pryor project? Is it, my understanding there is that the 45V credit is the crux of the economic uplift from Pryor. Is there some other economic monetary benefit you would get directly from the Pryor project?
Yeah, so the details and the economics of the project are still unknown, because like I mentioned, we're still working with EPC firms to get the right cost estimate of the CapEx. We're also still determining, should we do more solid oxide or should we do alkaline? So that technology will play a role in the CapEx because they have different efficiency in the way they operate. But at the end of the day, you're going to receive $3 a kilogram per kilogram of hydrogen produced, which is a big incentive. The idea is that should cover most of the CapEx and OpEx for the 10-year of operation. Then in addition to that, there are other benefits that you can get. One of them is, and that's our target, is that there will be customers willing to pay a premium for low carbon products because that helps them decarbonize the supply chain. And we believe that the industrial buyers of ammonia will be first to do that ahead of the ag users of ammonia. Take, for example, Windex. Windex is a very common glass cleaning household product, right? It has a small quantity of ammonia in it as the cleaning agent. So companies that make it, they have publicly said that they can see in the future, you go to the supermarket to buy a bottle of Windex and you have your conventional Windex at 99 cents a bottle, and you have a bottle right next to it that looks exactly the same. It has the same chemical composition, but it has a label there that says made with 80% lower carbon intensity or 90% lower carbon intensity, and it costs you $1.10. If people truly believe that is a real carbon intensity reduction, they will have no problem paying an additional 10 cents for that bottle. Well, companies believe that incremental 10 cents on that bottle could help for paying for thousands of dollars a ton on the supply chain to decarbonize that product. So at the end of the day, it's going to be passed on to the end users or consumers like us. But that's how they're thinking about it. Now, In the event that industrial users of ammonia are ready to pay a premium, or ag users of ammonia are ready to pay a premium for the ammonia ton, we can always register, in the case of El Dorado, the carbon tons that are being offset, and then sell offset in the voluntary market. And in the case of Pryor, we can register the abated tons or the non-emitted tons per ton of ammonia, because you have a facility today that has a certain carbon intensity, and that carbon intensity will go down for these 30,000 tons, essentially down to zero. And then you can see that avoidance, which is about 60,000 tons of CO2 a year. You can register that and sell them in the voluntary markets, which the last data point we have is from 2019, because they're about a couple of years in the rears and now got impacted by the COVID pandemic as well. But in 2019, they sold for about $14 a ton for CCS projects. Obviously, as people look into decarbonize and they participate more and more in these voluntary markets, that price is unavoidably going to increase. So say you get $20 a ton in 2025, that could be $40 a ton in per ton of ammonia, in terms of additional benefit for doing these projects.
On that 30,000 ton partial conversion at Pryor, how many kilograms of hydrogen would you be converting? I don't know what the conversion is, assuming you could get the 45V credit.
Yeah, so to make a ton of ammonia, you need 177 kilograms of hydrogen. So 30,000 tons, I think, if I recall correctly, somewhere between 5.2 and 5.3 million kilograms of hydrogen a year.
Okay, yeah, that's helpful. Just switching gears to El Dorado, you I think during the presentation you said there's a 12 million or a 15 million EBITDA positive impact from are you splitting 45Q credits with the project sponsor? Is it a fixed fee? Where does that 12 to 15 million come from? Is that somehow volume related? I just wanted to understand that.
Yeah. So it's essentially coming from selling a product that today is being invented, right? So the way the 45Q works is that the owner of the capture facility, the compression, dehydration, and more compression, is the entity that receives the 45Q. So in our case, Lapis Energy will receive the 45Q, and they'll pay us a dollar amount per ton of CO2 that gets sequestered. And that amount is a percent of the 45Q. So when the 45Q goes up 2-3% with inflation, our payment also goes up 2-3% with inflation. That's how the deal is structured, but the deal could have been structured in any other way, right? I believe the deal with that got announced, CF Industry and ExxonMobil. In that particular one, CF will build the capture facility, so CF will receive the $85 a ton 45Q, and then in turn they'll pay Exxon a fee for the transportation on the pipeline and the sequestration of that CO2 ton, and then custody of that ton under the subsurface. That's how our project was built. So yeah, it is essentially a sale of CO2 that today we're venting.
Gotcha. A while back, a couple of quarters back, there was some discussion about some USDA funding being available for, I think, a brownfield expansion at El Dorado. Is that still something the company is working on, or has that been subsumed by these other projects?
Yeah, maybe I'll jump in there on that one. So yeah, we applied for USDA funding as part of their to get a portion of the $500 million that they had earmarked for domestic fertilizer production expansion. We haven't heard back yet, other than they've received the application and it was complete to their satisfaction. But we do expect to hear back in the next couple of months on whether we've made it through to the next round or the next review.
Understood. Thank you.
We just passed the top of the hour a few minutes ago. Jacob, I've got one more question that's been asked here. Do you have time for that? And thank you, everybody, by the way. If you need to fall off, please do. Jacob, so you mentioned the 80-20 coal ammonia mix in Japan. Is the ammonia portion of that mix capped at 20%, or might it move up with more trials?
So the idea is that eventually we'll move up. I think they're kind of, and by the way, this isn't new. They've done a lot of lab scale testing. They've done a lot of pilot plant testing. There was one even done in Malaysia at a smaller power plant, and they're testing different type of injection mechanisms of how to inject the ammonia in the coal bay. I think the idea is that the way the policy in Japan is going to be set is that it's gradually going to be a shift with the net zero target of doing 100% ammonia. But between now and then, they can set policy at 20% for all companies and then move it up and 40% and higher and higher as we get closer to 2050.
Well, that's terrific. Thank you so much. I want to thank Jacob for joining us today and giving us this presentation and all the Q&A. I'd like to thank all the investors for joining us today as well. And Mark and Fred, and I see Cheryl, you're on the line. Thank you so much for joining us as well. If you have any other questions, I would encourage that you email them to Fred Buonocore at LSB Industries or myself. I'll be happy to forward that on so Jacob can answer those questions. And with that in mind, thank you again.
Thanks, Rob.
Coming us.
Thank you, everybody.
Research for LSB Industries is provided by Granite Research, a California-based investment advisor. Investors can access research publications and additional information at Granite Research's website at granite-research.com.